Welcome, y'all. Back to some more math funness here. We're talking about the tangents. So, we talked about tangent before. We talked about tangent in trigonometry, but we're talking about tangent as far as in a line. So, for example, here, like this. A tangent line, of course, is a line that exists out in space, but in relation to a circle, it touches that circle once. So, a line that's tangent to a circle touches the circle once at the point of tangency. That's that point right here. So, in this case, this is the point of tangency where the circle and the line meet. This is the point of tangency where the circle and the line meet. All right. According to this theorem, what it's saying is that anytime you draw a radius from the center to that point of tangent, it will always be a right angle. Always make a right angle right there. So anytime we draw it. So if the line of tangency is up here, the tangent line's up here, point of tangency, and I go radius from here to here, it makes a right angle right there every single time. But how is that relevant here? Well, good question. Here, we've seen this before. Anytime we have a right triangle, we use our Pythagorean theorem. Yeah, our Pythagorean theorem. Our a squared plus b squared equals c squared. Okay, so in this case, then, the distance from the center out to a random point on that tangent line, that's our hypotenuse. Right there. Now the question here is, what's the value of RQ? So we want to know the distance from this point out to this point out here. Now we do know what it is from O to R, because if it's 6 right here, it's also 6 right here. Our ultimate goal is to figure out just this little spot. So by using our Pythagorean theorem, we're going to call this C, the whole thing is C. We'll say, hey, 6 squared plus 8 squared equals C squared. All right, so we square that, you get 36 plus 64 equals C squared. You add that, you get 100 equals C squared. Square root that. C equals 10. So the whole thing is 10. Well, this is 6. That makes this 4. 4 right there. Now, this is some more information on this. You have interior common tangents. You have interior ones or exterior ones. Interior means, hey, if this one tangent line kind of goes diagonal like this and it touches the circle, it will touch the circle, tangentially. They are what we call an interior tangent right here, because it's going kind of like between them. Exterior tangents go outside, stay on the outside, whether on bottom or on top. You draw a tangent line up here. So there's exterior ones and there's interior ones. You kind of see these right here, kind of in bikes or in machinery mechanisms that go across like that. Not very often do you see that, except on some smaller. We have, if you ever look at the an engine has a lot of their belts that go like that. They have a small one running this way, and then it runs across to another one. That happens a lot as well. All right, now these common tangents are important because if, according to this theorem, it says that if you have some random point out in space and you draw two tangent lines to a circle, the distance from that point to the point of tangency is the same. It's the same. So the distance from here to here is the same as the distance from here to here. So that being said, when you have the same exterior point and you draw two tangent lines, and here's the thing, you can only draw two. You cannot draw no more tangent lines. FYI. Fun fact, you can never draw more than two tangent lines to a circle from one point of tangency, from the same one point. So I can't draw another line that we can. Anyways, back to this. So the segment, the distance from that point of tangency to the point of tangency to the exterior point on here is the same. So that being said, if we're solving for x, we will say x plus 15 equals 2x minus 5. So to solve for x, minus x minus x plus 5 plus 5. You end up getting 20 equals x. Now, solve for x, 20. Now, the distance would be then 20 plus 15, 35. Okay, 2 times 20 is 40, minus 5 is 35 as well. So, to reiterate this, if you have one exterior point going to the same circle, that distance is the same. Now that matters because, now we talked about this before. polygons that are circumscribed about the circle, or the circle being inscribed. So here we have a triangle. We want to find the perimeter of this triangle, what is circumscribed about. So it's, you drew the triangle outside the circle. So to figure this out, well, just look. Okay, distance from here to here is 10. That means the distance from here to here is also 10. Distance from this exterior point to here is 2, then from here to here is also 2. Now, if the whole thing is 8, and then from here to here is 2, then from here to here is 6, making this 6 as well. So as we add this up, we got 10 plus 10 is 20. Well, actually, let's do the whole thing. This whole side is 16, this whole side is 8, and this whole side is 12. So 12 plus 8 is 20, plus 16 makes it 36. 36 all the way around. So the perimeter of the triangle is 36. So you guys kind of try this one. I'm going to stop talking for 5 seconds, or you could pause it. All right. So let's look at the same idea here. So from here to here is 6, means from here to here it's also 6, because it's the same exterior point. 5 and 5, 5 and 5 this way, so it's 5 right here. The whole thing is 13, so 13 minus 5 puts me at 8, and then from here to here is 8. And then we just add those up. So we got 14, 11, 10, and 13. The 10, 20, 37, 48. 48. All right, y'all. Hope that helps. Catch you on a different day. Bye.